Look at the lamp nearest you. The light falling on your hands right now is roughly 1/10 trillionth of the energy our species commands in a single second. And yet, on the cosmic ledger that ranks civilizations by the power they wield, we have not even finished the first rung. A Soviet astronomer drew that ladder in 1964. 60 years later, we are still standing beneath it, looking up. Tonight, you're going to descend through the full architecture of that ladder, from the number etched at its base to the planetary energies waiting at its first step, and understand why the gap between where we are and where we need to be is one of the most quietly profound measurements in all of science. Before we dive in, if you love exploring the mysteries of civilization and cosmic scale as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. There is a number that defines us, not by who we are or what we have built or what we believe, but by how much energy we can command at any given moment. That number, as of the most recent calculations, is approximately 0.73. It is a small number. It sits modestly on a scale that runs from 0 to 3 and beyond. It represents, with more precision than most measurements of civilization have ever managed, exactly where the human species stands in the cosmos. And the closer you look at it, the stranger it becomes. The man who invented the ladder that gives this number meaning was Nikolai Kardashev, a Soviet radio astronomer working in the early 1960s in a world electrified by the space race. Kardashev first outlined his scale in a paper presented at the 1964 Burakhan Conference in the Armenian SSR, a scientific meeting that reviewed the Soviet radio astronomy space listening program. The paper was titled, in Russian, Transmission of Information by Extraterrestrial Civilizations. Kardashev was not primarily interested in humanity. He was interested in what to listen for. He was trying to work out, in the most rigorous terms available to him, what a genuinely advanced alien civilization might look like from a distance, what kind of signal it might broadcast, and what kind of energy budget it would need to broadcast it. His insight was deceptively simple. Energy consumption serves as a universal proxy for technological capability. As a species grows more sophisticated, it needs more power. More power to sustain larger populations, run more complex systems, project force, store information, resist entropy, and reach outward into space. The amount of energy a civilization controls tells you, more reliably than almost any other metric, how far along the developmental road it has traveled. So Kardashev proposed a classification. The scale categorizes civilizations into 3 types: Type 1, Type 2, and Type 3, with each level representing a civilization's ability to harness and control energy at increasing scales, planetary, stellar, and galactic, respectively. Pause here, because this is worth letting settle before anything else. 3 types: planetary, stellar, galactic. And we are not yet at the first one. We are not a Type 1 civilization. We are not close to being a Type 1 civilization in any unit of time that a human lifetime can comfortably hold. We are, right now, a civilization still burning the buried carbon of ancient life to heat our buildings and move our vehicles. A civilization that, for all its satellites and microchips and deep-sea cables, has mastered roughly 7/10 of the first rung on a 3-rung ladder. And those rungs do not grow linearly. They grow by factors of 10 billion. This is the picture most people never quite see. When someone mentions the Kardashev scale in conversation, the mental image that tends to form is one of proximity. We're almost there, a few centuries of progress, and humanity will cross that threshold into Type 1, whatever that means. The textbook version of this story is a story of comfortable momentum. We are growing, We are innovating. The curve is bending in the right direction. Give it a few hundred years, and the math will sort itself out. But here's what the textbook version doesn't tell you. The math is not sorting itself out on that schedule. The gap between a 0.73 civilization and a 1.0 civilization is not a gap of degree. It is a gap of a different kind. It requires not just more energy, but a different relationship with energy entirely. And the obstacles standing between us and that relationship are not primarily technical. They are political, ecological, and perhaps existential. The closer you look at the actual numbers, the more the word almost begins to dissolve. So where does this number, 0.73, come from? And what does it actually mean? The original Kardashev scale did not have decimals. It had 3 types, defined in broad qualitative terms. Use all planetary energy, use all stellar energy, use all galactic energy. That framework was powerful as a conceptual scaffold, but it left an enormous unaddressed space. Where does a civilization like ours fit? We are clearly not at type 1, but we are clearly not at 0 either. We have harnessed the atom, mapped the genome, threaded the continents together with light. We are something. But what? The man who answered this question, who gave us the precise decimal that now defines our civilizational position, was Carl Sagan. Carl Sagan furthered the Kardashev scale with data extrapolation and proposed a continuous function quantifying the Kardashev scale. Sagan defined intermediate values by interpolating and extrapolating the values given for types 1, 2, and 3, producing the formula K equals log P minus 6/10, where K is a civilization's Kardashev rating and P is the power it consumes in watts. Sagan believed that the Kardashev scale was too spread out and that the gaps between the 3 levels were so large that a finer gradation was needed. He defined human civilization as a type 0.7 using this scale, writing in the 1970s when global energy consumption was around 10 terawatts. Humanity's civilization type, as of 1973, was about 0.7, using an average power consumption of 10 terawatts as the value. Half a century later, the number has barely moved. As of 2018, global power consumption was approximately 18.4 terawatts, corresponding to a Kardashev rating of roughly 0.73. A 2023 paper published in Scientific Reports, using machine learning models to project global energy trends, estimated our current standing at approximately type 0.73 on the Kardashev scale, though the precise figure varies depending on energy accounting methodology. The most recent assessments, drawing on 2024 and 2025 energy data from the International Energy Agency, leave us in essentially the same neighborhood, somewhere between 0.72 and 0.74, depending on which energy figures you use and how you account for efficiency losses in the conversion of primary fuels to useful work. Take stock of where we are. In 50 years during which we have invented the internet, decoded the human genome, built the International Space Station, sequenced proteins with artificial intelligence, and planted solar panels across millions of acres of desert, our Kardashev number has risen by approximately 0.03 of a point, from roughly 0.70 to roughly 0.73. The arc of progress is real, but it is far slower than the popular imagination tends to assume. And here is what a Type 1 civilization actually requires. For Earth, the total solar energy incident on the planet is approximately 1.74 times 10 to the 17th power watts. That is 174,000 terawatts of continuous solar power, washing over the surface and upper atmosphere of this planet every second of every day. The Earth intercepts roughly 173,000 terawatts continuously. This is more than 10,000 times the world's total energy consumption. A full Type 1 civilization, as Kardashev's framework implies, would need to command energy on the order of 10 to the power of 16 watts, roughly 10,000 terawatts, which sits comfortably within the lower bound of what solar energy alone delivers to our atmosphere. We currently use roughly 18 to 19 terawatts of primary energy. Humanity currently consumes around 2 times 10 to the 13th power watts, placing it significantly below Type 1. The Type 1 threshold sits 5 orders of magnitude above our current use. That is not a rounding error. That is a gap so wide that closing it within any timescale less than several centuries would require rates of energy expansion that have no historical precedent and would generate ecological consequences that would reshape the planet long before we arrived at our destination. The textbook answer says, "We are making progress, and progress compounds." That picture is almost entirely incomplete once you look at what progress actually means in the context of this scale, and once you understand the multiple interlocking constraints that stand between our current number and the one we would need to reach. Progress is real, but the gap is not closing at the rate that comfortable narratives of technological optimism suggest. It is closing in some dimensions and barely moving in others, and in a few dimensions, it may actually be getting harder. This is what the rest of our time together will explore, layer by layer, from the physics of energy itself, to the economics of transition, to the civilizational sociology of coordination, to the deepest philosophical question the Kardashev scale quietly poses. What kind of species would we need to become in order to reach that first rung? Because the answer to that question is not primarily a technical one. But before we get there, we need to fully understand the scale itself, not just as a number, but as a concept with deep roots in physics and with implications that ramify outward into cosmology, the search for extraterrestrial intelligence, and the long arc question of what civilizations actually are. Nikolai Kardashev was born in 1932 in Moscow and spent the early part of his career at the Sternberg Astronomical Institute, where he worked from 1955 through 1967, before later joining the Space Research Institute and ultimately leading the Aerospace Center of the Lebedev Physical Institute. He was drawn to the largest questions: the structure of the universe, the nature of quasars, the possibility that other minds existed among the stars. Kardashev was part of a team searching for extraterrestrial signals in 1963, and he believed that there could exist alien civilizations far more advanced than humans. He proposed a scale to classify such civilizations based on the amount of energy resources they could use in interstellar communications. The scale was not, in his original conception, a roadmap for human development. It was a tool for detection. If you want to search for alien civilizations, you need to know what to look for. And the most obvious signature of an advanced civilization would be the waste heat, the electromagnetic leakage, the physical modifications to its planetary or stellar environment that an enormous energy budget would inevitably produce. The logic was elegant. A civilization that controls the energy of a star would be, by any measure, enormously visible from interstellar distances. Its waste heat alone, the inevitable thermal entropy of running any energy-intensive system, would create an infrared signature detectable across many light years. Freeman Dyson, the British-American physicist, had proposed in 1960, just 4 years before Kardashev's paper, The concept of a megastructure that would become one of the iconic thought experiments in SETI research. A shell or swarm of structures surrounding a star, capturing its entire energy output. We scan the skies for techno-signatures, the waste heat of Dyson spheres, the flicker of alien megastructures. Kardashev's scale gave these searches a quantitative framework. A Type 2 civilization would be building Dyson spheres. A Type 3 civilization would have restructured an entire galaxy. And a Type 1 civilization, well, that would be one that had merely mastered its home planet. Merely. That word deserves to sit in the air for a moment. Mastering a home planet. Controlling every joule of solar energy that falls on the surface. Harvesting wind and tide and geothermal heat. Channeling the force of volcanoes. Manipulating weather systems. Managing the hydrological cycle. Extracting fusion energy from the hydrogen in seawater. That is what Type 1 means. Not a civilization that has a few good solar farms and some offshore wind turbines. A civilization that has achieved complete planetary energy mastery. Type 1 represents a civilization capable of using energy resources on a planet-wide scale, or equivalent to the entire power consumption of the planet, harnessing both the energy that reaches the planet from its star, such as solar energy, as well as all energy the planet can produce, such as wind, hydroelectric, and geothermal energy. Something here deserves attention. The original 1964 paper defined Type 1 much more conservatively. Kardashev initially defined Type 1 as energy consumption on the order of approximately 4 times 10 to the 12th power watts. That is 4 terawatts, less than a quarter of what we currently consume. By Kardashev's original definition, we might already be approaching the lower edge of Type 1. But the definition has since evolved as scientists work to align the scale with a more physically meaningful standard. The modern consensus, following the work of physicists like Guillermo Lemarchand and the mathematical framework formalized by Carl Sagan, sets the Type 1 threshold at 10 to the power of 16 watts, 4 orders of magnitude above Kardashev's original number and roughly 5,000 times our current consumption. This definitional evolution matters enormously because it changes the scope of the question. If we use the original, narrower definition, humanity might be decades away from Type 1. If we use the modern, physically grounded definition, the one that requires genuine planetary energy mastery, we might be centuries away or more. The question, how close are we, does not have a single answer. It has a range of answers, and the range depends critically on which definition you accept. Ascending the Kardashev scale isn't really a realistic goal in the short term. The scale is more a crude guide for thinking about how a technological civilization could grow and what its ultimate limits could be. This is one of the first places where the comfortable narrative cracks. Everyone knows we're at 0.73. The simple version of this story says, just keep growing, add renewables, build bigger grids, and eventually the number ticks up to 1.0. But here's what almost nobody tells you about the mathematics underneath. The Kardashev scale is logarithmic. Moving from 0.73 to 1.0 on a logarithmic scale is not moving 27% of the way along a line. It requires multiplying our total power consumption by roughly 500 times our current energy use. Hold that number for a moment. Not double, not 10 times, not 100 times, 500 times the energy we consume today, delivered continuously, without pause, without significant environmental cost, to a species that currently finds it politically contentious to add wind turbines to rural landscapes. The scale tells us exactly where we are and exactly how far we have to go. And the distance between those 2 points is not primarily a story of watts and joules. It is a story of choices, constraints, and the peculiar stubbornness of civilizational inertia. That story begins with energy itself, with what we currently burn, where it comes from, why we burn it, and what it would take to burn something fundamentally different. The world, right now, runs on ancient sunlight. That phrase is not poetry. It is chemistry. When you burn a liter of gasoline, you are releasing carbon that was pulled from the atmosphere by photosynthetic organisms, somewhere between 100 million and 300 million years ago, buried under sediment, compressed under heat and pressure across geological time, and then extracted from the ground by machinery, burning more of the same material to power the extraction. The entire edifice of modern industrial civilization, its factories, its shipping lanes, its data centers, its hospitals, its wars, rests on a foundation of fossilized biology. We are, in the most literal sense, living off a planetary inheritance that accumulated over hundreds of millions of years, and we are spending it at a rate that would exhaust the account within a few human generations. This is the baseline from which any serious discussion of the Kardashev scale must begin. Not from some idealized future state of fusion reactors and orbital solar collectors, but from the actual, measured, deeply human reality of where our energy comes from today. Because you cannot understand how far we are from Type 1 without first understanding what Type 0.73 actually looks like. Not as an abstract number, but as a physical fact woven into the texture of daily life on this planet. The International Energy Agency's Global Energy Review for 2025, drawing on data from 2024 and updated through early 2026, paints a picture of a world energy system in genuine transition, but also in genuine tension with itself. Global energy demand grew by 2.2% in 2024, faster than the average rate over the past decade. Global electricity consumption rose by nearly 1,100 terawatt-hours in 2024, more than twice the annual average increase over the previous decade, and the largest ever single-year increase outside of economic rebound years. The increase was more than Japan's entire annual electricity consumption, added to the global total, in a single year. And yet, for all of this growth, the picture of where that energy comes from remains stubbornly familiar. The share of fossil fuels in global energy supply has been stuck for decades around 80%, only now beginning to edge downward. Oil's share of total energy demand fell below 30% for the first time ever in 2024, 50 years after peaking at 46%. That is genuine progress. But it is progress measured in single percentage points across half a century, while the absolute quantities continue to grow. Take a moment to feel the scale of this. Imagine the entire industrial output of Japan. Every factory, every car, every heated home, every hospital, every bullet train, every data center in that vast, dense, technically sophisticated nation of 125 million people. And imagine adding that entire system to the global energy grid in a single calendar year. That is roughly what the 2024 increase in electricity consumption represents. And renewables accounted for the largest share of the growth in global energy supply that year, 38% of new supply, followed by natural gas at 28%, coal at 15%, and oil at 11%. The direction is right. The speed is not yet enough. To appreciate why speed matters so much, you need to understand what a Type 1 civilization would actually require. Not in abstract watts, but in physical infrastructure deployed at planetary scale. The solar energy intercepted by Earth at its upper atmosphere amounts to approximately 173,000 terawatts continuously. Of this, roughly 30% is reflected back to space by clouds and the albedo of the surface, leaving about 122,000 terawatts actually absorbed by the planet. The remainder drives weather systems, the water cycle, ocean circulation, photosynthesis, and the biosphere as a whole. It warms the surface to temperatures that allow liquid water to exist. It powers the wind and the rain and the slow circulation of the deep ocean. The entire living system of this planet runs on a fraction of that 122,000 terawatts, drawing from the solar income continuously deposited into the account. We currently use approximately 18 to 19 terawatts of primary energy. Total. Everything. Every barrel of oil pumped from the Arabian Peninsula. Every ton of coal dug from mines in Australia and China. Every cubic meter of gas extracted from beneath the North Sea. Every terawatt hour generated by nuclear plants in France, by hydroelectric dams in Brazil, by wind farms in the North Sea, and solar arrays in the Mojave Desert and the Gobi. All of it together. 18 terawatts. Compare that to 173,000. The ratio is slightly less than 1 in 10,000. We are using, across our entire civilization, less than 1/100th of 1% of the solar energy that falls on this planet every second. Carl Sagan estimated that 1970s, humanity at roughly 10 terawatts was equivalent to 0.16% of the power available on Earth. We have grown since then, but the fraction remains vanishingly small. The sunlight that reaches Earth every day dwarfs all the planet's other energy sources, clearly sufficient in scale to meet all of mankind's energy needs, if it can be harnessed and stored in a cost-effective way. There is something almost paradoxical in this situation. We sit at the center of a power source so abundant that it dwarfs our needs by 4 orders of magnitude. And yet we find ourselves burning fossilized biology because the engineering of capturing that abundance has, historically, been too expensive and too intermittent to compete with simply digging up ancient carbon and setting it on fire. The gap between us and Type 1 is not a gap caused by scarcity. It is a gap caused by the mismatch between the form in which energy arrives and the form in which we need to use it. This is worth pausing on because it cuts against the common intuition. The popular narrative of civilizational energy limits often frames the problem as one of running out. Running out of oil, running out of gas, running out of the buried reserves that have powered the industrial age. And while depletion is a real concern on geological timescales, it is not, in any strict sense, the reason we are at 0.73 rather than 1.0. We are at 0.73 because we have not built the systems necessary to capture and deploy the energy that falls freely on us every second. The problem is not supply. The problem is infrastructure, storage, grid architecture, political will, and the trillion-dollar inertia of existing fossil fuel systems whose physical plant has been paid for and whose supply chains have been optimized over more than a century. So, what does the current energy infrastructure actually look like at the numbers level? Installed solar PV capacity worldwide reached an estimated 2.2 terawatts by the end of 2024, following a record year in which solar PV additions rose by almost 30%, totaling about 550 gigawatts of new capacity. In 2025, solar PV posted its largest ever single-year generation increase, adding 600 terawatt-hours of electricity, more than doubling its output compared to 2022, and pushing solar's share of total global electricity generation above 8% for the first time. Solar PV additions in 2024 alone rose by nearly 30% year over year, and growth in solar PV met more than 1/4 of global primary energy demand growth in 2025. The first time on record that a modern renewable source contributed the largest share of global energy demand growth. These are genuinely extraordinary numbers. They represent a pace of solar deployment that would have seemed implausible a decade ago, when the cost of photovoltaic panels was still high enough to require substantial subsidies in most markets. The cost curve for solar has been one of the great technology success stories of the early 21st century, falling by more than 90% between 2010 and 2024, driven by manufacturing scale, materials science improvements, and the compounding effects of learning by doing in factories across China, Southeast Asia, and increasingly other regions. But here is the deeper picture that those numbers also reveal when you hold them against the scale of what Type 1 actually requires. 2.2 terawatts of installed solar capacity worldwide. That sounds large. And it is large by any human-scale comparison. It is more capacity than existed in all of nuclear power globally just a decade ago. But a Type 1 civilization would need to command on the order of 10,000 terawatts continuously, not as installed capacity, but as delivered power. If we were to supply that from solar alone, which we would not, but as a thought experiment, at current efficiency rates and accounting for the day-night cycle and weather variations, you would need something on the order of 50 to 100,000 terawatts of installed solar capacity. We have 2.2. We are building roughly 0.55 per year. At that rate, the math is not encouraging. This is the first real encounter with what might be called the compounding gap, the phenomenon in which a problem that looks manageable in the near term reveals itself, on closer examination, to grow faster than the rate at which we are currently solving it. Some researchers think this gap can be closed by exponential growth in clean energy deployment, which has indeed been accelerating. Others point to the structural limits on how fast any physical infrastructure build-out can proceed, regardless of how much money or political will is applied. The raw material constraints alone, the lithium, cobalt, silicon, rare earth elements required for batteries, solar panels, and wind turbines, represent supply chain bottlenecks that cannot be resolved simply by wanting to resolve them more urgently. Consider lithium. Battery storage was the fastest growing power sector technology in 2025, with roughly 110 gigawatts of new battery storage capacity added during the year, exceeding the largest ever annual capacity additions for natural gas. That is remarkable. But lithium-ion batteries, at current energy densities, face physical limits on how much storage they can practically provide per ton of material. The transition to a fully electrified, renewables-powered civilization would require mining volumes of lithium, cobalt, copper, and rare earths that are, by current estimates, many times larger than present production. And mining at that scale carries its own ecological consequences, its own geopolitical complications, its own temporal constraints. This is not a counsel of despair. It is a map of the terrain. The energy transition is real, and it is accelerating. But the distance from 0.73 to 1.0 on the Kardashev scale is not a distance that honest accounting can compress to a few comfortable decades. Now we turn to the deeper structure of the problem, the civilizational constraints that sit beneath the purely technical ones. The transition from Type 0 to Type 1 is considered the most dangerous period in a civilization's development. It involves navigating the adolescence of technology, where nuclear weaponry, biotechnology, and artificial intelligence exist. But the planetary unity and wisdom to control them perfectly do not. The energy limitations of a Type 0 society are dictated by the available chemical potential of the planet's crust, and the primitive capture of solar radiation. Rockets rely on chemical combustion. Communication is global but fragmented. The defining characteristic of this stage is the struggle to unify planetary resources and transition to sustainable, high-density energy sources. Moving up the Kardashev scale is not merely an engineering challenge, it is a sociological transformation. A Type 0 civilization is fragmented, tribal, and competitive. Resource scarcity drives conflict. The transition to Type 1 requires a fundamental shift toward cooperation. Planetary management cannot function if nations are at war. It necessitates a global governance structure or a unified resource allocation system. And that requirement is not incidental to Type 1. It is definitionally embedded in it. Think about what complete planetary energy mastery actually implies. It implies a civilization that has agreed, at some level, to manage the energy budget of an entire world as a common resource. It implies infrastructure spanning every continent, every ocean, every climate zone. Infrastructure that does not respect national borders, that requires maintenance and coordination across political systems that currently cannot agree on basic emissions targets, let alone the wholesale restructuring of the global economy. It implies weathering geopolitical disruptions that might damage or destroy critical nodes of a planetary energy grid. It implies solving, in practice rather than in theory, the problem of energy storage at scales that can smooth out not just daily cycles, but seasonal variations in solar and wind availability. Consider what seasonal storage means in physical terms. Solar energy in Northern Europe in December delivers roughly 1/10 the power per square meter that it delivers in June. Wind is more consistent, but also variable. Balancing a planetary grid across seasons, across hemispheres, across years of variable weather requires either vastly overbuilt generation capacity, very long-distance transmission infrastructure connecting complementary climate zones, or storage technologies capable of holding energy across months, not hours. We do not currently have a commercially viable solution to seasonal energy storage. We have proposals: hydrogen, ammonia, pumped hydro, iron-air batteries, compressed air. But none has yet demonstrated the economic and scalability profile required to operate at planetary scale. These are not unsolvable problems. Some researchers think the combination of green hydrogen and existing grid infrastructure could bridge the seasonal storage gap within decades, given sufficient investment. Others argue that the structural costs of hydrogen production, transport, and reconversion are prohibitive at the scale required, and that alternative approaches, geothermal baseload, next-generation nuclear, or as yet uninvented storage technologies, will be necessary. What both camps agree on is that the solution is not yet in hand. Here is where honest accounting produces its most vertigo-inducing number. A 2023 machine learning study published in Scientific Reports modeled global energy consumption across multiple scenarios and projected that humanity will reach a Kardashev value of approximately 0.7449 by the year 2060. 35 years from now, with a humble average annual growth rate in our K-value of approximately 0.042%. At that rate, reaching 1.0, requiring, remember, a roughly 500-fold increase in power consumption, would take not decades, but centuries. Even under optimistic scenarios involving the widespread deployment of nuclear fusion and accelerating renewable build-out, the timeline to genuine Type 1 status stretches well into the 22nd century and potentially well beyond. Physicist Michio Kaku estimated that if humanity increases its energy consumption by approximately 3% annually, we might reach Type 1 within a few hundred years. But 3% annual energy growth, compounded indefinitely, carries its own consequences. Because energy use is not thermodynamically neutral. Every terawatt of additional power consumed on or near the surface of Earth generates waste heat, alters albedo, interacts with atmospheric chemistry, and modifies the climate system. Long before we reach the 10,000 terawatts that Type 1 requires, we would encounter hard physical limits imposed by the planetary heat budget. This is the constraint that almost never appears in popular discussions of the Kardashev scale, and it deserves considerably more attention than it typically receives. Take a slow breath here. Stay with this for a moment. The surface temperature of Earth is a balance. Energy in, primarily solar, versus energy out, primarily thermal radiation back to space. The average global temperature is what it is, because those two flows are, over time, approximately in equilibrium. When you add waste heat to the surface, not by changing the composition of the atmosphere, but by simply dissipating the products of energy use as heat on the surface, you disturb that equilibrium. The effect is small at current consumption levels. 18 terawatts, spread across the global surface area, is tiny compared to the 122,000 terawatts of solar energy absorbed by the planet. But at 10,000 terawatts, which is where Type 1 sits, the waste heat of civilization itself begins to meaningfully affect the global temperature budget. At that level, even a perfectly carbon-free civilization running entirely on fusion or orbital solar energy would still be warming the planet through waste heat alone. This is what some researchers call the thermodynamic ceiling, the upper limit imposed not by resource scarcity, not by atmospheric chemistry, but by the simple fact that any energy you use eventually becomes heat, and this planet has a finite ability to radiate that heat back to space. The thermodynamic ceiling does not make Type 1 impossible. It makes Type 1, in its fullest expression, something that requires not just building new infrastructure, but redesigning the fundamental relationship between civilization and planetary physics. A Type 1 civilization would need to manage its waste heat with the same sophistication with which it manages its energy generation. It would need technologies for radiating excess heat into space more efficiently, or for locating energy-intensive processes in orbital or extraterrestrial environments, where the heat can be dissipated into the cold sink of space rather than into the surface atmosphere. These are not near-term engineering challenges. They are the hallmarks of a civilization that has moved so far beyond our current technical capability that the label Type 1 begins to feel an almost misleadingly modest. So the picture so far, roughly halfway through laying our foundation, looks something like this. We are at 0.73 on a scale that requires us to reach 1.0 before we can even claim to have mastered our own planet. The gap between those two numbers requires a roughly 500-fold increase in energy consumption. We are currently growing our energy consumption by approximately 1 to 2% per year, with the clean energy fraction of that growing considerably faster. We have 2.2 terawatts of solar capacity installed globally, adding roughly half a terawatt per year. We face material constraints, storage constraints, grid architecture constraints, political and coordination constraints, and ultimately the thermodynamic constraint of the planetary heat budget. And yet, and this is where the story becomes genuinely interesting, there are reasons to believe that the path to Type 1 is not simply a matter of scaling up what we already do. There are technologies on the horizon, and one in particular, that could change the shape of the problem in ways that no simple extrapolation from current trends can capture. One technology that has been perpetually 2 decades away for nearly 70 years, and which is now, for the first time in the history of physics, generating experimental results that make the optimism feel earned rather than merely habitual. That technology is nuclear fusion, and understanding why it matters to the Kardashev question requires understanding first why every energy technology we currently use is, in some sense, still a derivative of the same ancient stellar process, and why fusion represents something genuinely different in kind. Every energy source available to human civilization is, ultimately, a form of stored or redirected solar energy, with one exception. Fossil fuels are ancient photosynthesis, solar energy captured by organisms hundreds of millions of years ago, concentrated and stored in chemical bonds, now released by combustion. Hydroelectric power is rainfall, water lifted by solar evaporation, now falling back through turbines. Wind is atmospheric circulation driven by differential solar heating. Biomass is contemporary photosynthesis. Even ocean thermal energy conversion harvests the temperature gradient between sun-warmed surface water and cold deep water. Nuclear fission is the exception. Uranium and thorium, the fuels for fission reactors, were forged in the supernova that preceded the formation of our solar system. They are legacy energy from stellar explosions that occurred before the sun existed. Fission extracts that primordial energy by splitting heavy nuclei. It is not solar. It is, in a sense, interstellar. And as of early 2025, there were 62 nuclear reactors under construction in 15 countries around the world, with a total capacity of approximately 64.5 gigawatts, representing a modest but genuine nuclear renaissance after decades of political stagnation following the accidents at 3 Mile Island in 1979, Chernobyl in 1986, and Fukushima in 2011. Nuclear power generation reached a new high in 2025 and continued to rise, fueled by recovery in French nuclear output, restarts in Japan, and new reactors entering operation in China, India, Korea, and other countries. But fission, for all its merits, carries the shadows of those accidents in its political history, and carries also the unresolved challenge of long-lived radioactive waste and the material constraints of uranium supply at civilizational scale. Fission can be part of the path to Type 1. Most researchers think it will need to be, but fission alone, scaled to the consumption levels Type 1 requires, would create waste management challenges of breathtaking proportions. Fusion is different. Nuclear fusion, the process by which light nuclei, primarily isotopes of hydrogen, are forced together under extreme conditions to form heavier nuclei, releasing enormous amounts of energy in the process, is the engine that has powered the sun for 4.5 billion years. It is the process that converts matter into energy according to Einstein's famous relationship, releasing roughly 6 times more energy per unit of fuel than fission, and producing no long-lived radioactive waste. Its primary fuel, deuterium, can be extracted from ordinary seawater, making it effectively inexhaustible on any human timescale. A cubic meter of seawater contains enough deuterium to produce, through fusion, the energy equivalent of hundreds of tons of oil. The world's largest fusion experiment, the ITER project, International Thermonuclear Experimental Reactor, located in Kardashev in southern France, represents the largest international scientific collaboration in history, involving 34 nations through 7 formal member parties and decades of engineering. ITER is designed to demonstrate net energy gain from fusion at scale for the first time. Its construction has been slower and more expensive than originally projected, a story that will feel familiar to anyone who has followed fusion research over the past half-century. But as of 2023, experimental plasma operations were approaching, with the full-scale test of fusion energy expected to follow in the subsequent decade. Some researchers look at the ITER timeline and see a technology finally within reach after 70 years of patient incremental progress in plasma physics. Others point to the long history of fusion optimism, the joke that commercial fusion has always been 20 years away and has been for 50 years, and argue that ITER, even if successful, represents only the scientific proof of concept, not the commercial engineering reality. The first commercially viable fusion power plant would need to demonstrate not just net energy gain, but economic competitiveness with increasingly cheap solar and wind. That is a different and considerably harder challenge. And here is where the Kardashev perspective offers a reframe that pure engineering analysis tends to miss. The question is not only whether fusion can compete with solar on a levelized cost of energy basis in a specific market in 2050. The question is whether, in the second half of this century and beyond, fusion can serve as the high-density baseload power source that enables a civilization to command continuous, location-independent power at scales that intermittent renewables, even with sophisticated storage, may struggle to match. Type 1 is not just about having enough energy on average. It is about having enough energy everywhere, at all times, reliably, including in places where solar irradiance is low, where seasonal variability is extreme, where land is scarce, where a civilization needs to power systems in environments inaccessible to the surface infrastructure of a renewable grid. Fusion, if it works at scale, solves this problem in a way that no other clean energy technology currently in development can fully address. It is dense, meaning a small physical plant can produce enormous power. It is location independent, meaning it can operate in cities, at sea, at the poles, in space. It is continuous, meaning it does not need to be backed up by storage to handle variability, and it is effectively inexhaustible. This is why some researchers think fusion is not merely a nice addition to the energy mix, but a civilizational enabling technology. One of the relatively rare innovations in history that expands the frontier of what is physically possible for a technological species, rather than simply optimizing within an existing frontier. It could be. It could also fall short of that promise, technically or economically, in ways we cannot yet fully predict. What we can say with confidence is that the question of fusion's viability is one of the central open questions in the story of humanity's progress along the Kardashev scale. A question whose answer, one way or the other, will shape the trajectory of our civilization across the next century in ways that no political decision, no market force, and no individual technological innovation of a more incremental kind is likely to match. Step back, briefly. We have now laid the full foundation of what the Kardashev scale is, where we sit on it, and why the gap between our current position and Type 1 is both larger and more structurally complicated than popular intuition tends to suggest. We have seen the numbers: 0.73, 173,000 terawatts of solar income, 18 terawatts of current consumption, a roughly 500-fold gap. And we have begun to see the shapes of the obstacles that give those numbers their weight. The fossil fuel inheritance, the acceleration of renewables and its material constraints, the thermodynamic ceiling, the political challenge of coordination at planetary scale, the promise and uncertainty of nuclear fusion. Now we go deeper. Each layer we descend into reveals a different dimension of the same fundamental question. What would it actually take for a species like ours to become genuinely planetary in its energy reach? The next layer is the one that most energy discussions skip over almost entirely: the layer of energy efficiency and the radical possibility that the Kardashev scale itself may be asking the wrong question. Picture yourself standing in a room full of candles. not dozens, not hundreds. Imagine a room so full of burning candles that the heat is palpable on your skin, the air shimmers, and the wax is pooling on every surface. Now imagine that you are trying to read a book by this light, and that 90% of the energy being released in that room is going directly into heat that you cannot use, while the fraction actually illuminating your page is somewhere around 10%. And imagine that this ratio, roughly 10% useful work, 90% waste heat, is a reasonably accurate description of how the average fossil fuel power plant in operation today converts its fuel into the electricity that eventually reaches your lamp. This is the thermodynamic reality of the energy system we have built. It is a system characterized at every stage by enormous losses, and understanding those losses is essential to understanding both the Kardashev question and the genuine complexity of the transition we are attempting. When we say humanity uses approximately 18 to 19 terawatts of primary energy, we are measuring the energy content of the fuels we extract and burn, the chemical energy locked in coal and oil and gas before the conversion process begins. What actually reaches end users as useful work, light, motion, heat at the right temperature, digital computation, is substantially less. Energy intensity improvements continued to slow in 2024, improving at an average rate of only about 1% per year between 2019 and 2023. The global energy system, in aggregate, converts a significant fraction of its primary input into losses before any useful work is delivered. This creates a paradox that sits at the heart of the Kardashev question. The scale, as traditionally stated, measures total power consumption. But total power consumption includes all the waste, the heat losses in turbines, the line losses in transmission, the thermal losses in internal combustion engines, the standby power of billions of devices. If a more efficient civilization uses energy more cleverly, it might actually appear to move backward on the Kardashev scale, even while delivering more useful work to more people. A society that replaces a coal-fired power plant with a system that provides the same services with half the primary energy input has, by the raw Kardashev arithmetic, becomes slightly less advanced. Some researchers have pointed to this as a fundamental limitation of the scale. Not just a minor technical quibble, but a conceptual flaw that undermines its usefulness as a measure of genuine civilizational advancement. The Kardashev scale assumes ever-growing energy use. But what if true advancement means using energy more wisely, not just more abundantly? Advanced artificial intelligence, nanotechnology, and biological engineering could allow us to achieve more with less, leaving a lighter footprint on our world. The scale doesn't cover such things as advancing our understanding of ourselves, society, art, and much else of what makes us human. This critique is worth taking seriously. Consider computation. The amount of computational work performed by the global information technology sector has grown by many orders of magnitude over the past few decades, even as the energy required per unit of computation has fallen dramatically. Moore's law, the empirical observation that the number of transistors on a chip doubles approximately every 2 years, has driven efficiency gains in computing that dwarf almost anything achieved in any other energy-intensive sector. A modern smartphone performs calculations that would have required a room-sized supercomputer in 1980, consuming a fraction of 1% of the energy. If you measured the computational output of human civilization and plotted it against the Kardashev scale, you might conclude we had advanced far more rapidly than the energy consumption numbers suggest. But this line of argument, while genuine, runs into a hard limit. Computation is not the only thing a civilization needs. You cannot heat a home with a transistor. You cannot smelt steel with an algorithm. You cannot grow food in a data center. The physical infrastructure of civilization, the buildings, the transport systems, the agricultural systems, the industrial processes that make materials, requires energy in forms that do not compress elegantly into information-theoretic frameworks. The thermodynamic minimum for certain physical processes is set by physics, not by engineering creativity. You can improve efficiency, sometimes dramatically, but you cannot reduce the energy cost of melting iron to zero, regardless of how sophisticated your algorithms are. So the picture that emerges from careful analysis is nuanced. Efficiency improvements are real, they matter enormously, and they complicate any simple reading of the Kardashev number. A world in 2100 that uses 50 terawatts of primary energy but delivers twice the useful services of our current 18 terawatt world is, by any reasonable measure, more advanced than a world that uses 100 terawatts and wastes half of it. But ultimately, serving a civilizational population of potentially 9 or 10 billion people at genuinely high material standards, plus maintaining the kind of large-scale planetary management systems that Type 1 implies, will require more absolute energy, not less, even after efficiency gains are credited. The honest synthesis is this: efficiency buys time and reduces the size of the gap we need to close. It makes the thermodynamic ceiling less constraining. It lowers the material requirements for the energy transition. But it does not eliminate the gap. The distance from where we are to where Type 1 sits is still measured in hundreds of terawatts, and no amount of algorithmic cleverness removes the physical necessity of closing that distance with actual energy infrastructure. Now we turn to the dimension of this problem that operates at the largest scale and the slowest speed: the political economy of the energy transition, and why the challenge of coordinating 8 billion people across 200 nation-states around a common civilizational project is arguably harder than any of the engineering problems involved. Consider the following scenario. A technology exists that could, within 50 years, eliminate the need for fossil fuels entirely, produce energy at costs competitive with the cheapest existing sources, generate no carbon emissions, and provide reliable baseload power anywhere on Earth. This technology is not hypothetical. It is, with varying degrees of optimism, a description of what nuclear fusion might become. Now consider the following question. If that technology became available tomorrow, at zero additional cost, would humanity adopt it fast enough to meaningfully alter our trajectory on the Kardashev scale within this century? The answer, almost certainly, is no. And understanding why the answer is no requires understanding something about how energy systems work as economic and political structures, not just as physical ones. Energy infrastructure is among the most capital-intensive and long-lived of all human artifacts. A coal power plant built today has a design life of 30 to 50 years. A hydroelectric dam built in the 1960s is still generating power. A natural gas pipeline infrastructure, once built, shapes the economic logic of an entire regional energy system for generations. The capital investments embedded in existing fossil fuel infrastructure, the wells, the refineries, the pipelines, the power plants, the ships, the trucks, represent something on the order of tens of trillions of dollars globally. The organizations that own and operate this infrastructure have deep political relationships with the governments that permit and regulate them. The workers who depend on this infrastructure for their livelihoods have legitimate interests in its continuation. The tax revenues that flow from fossil fuel royalties and corporate profits fund public services in dozens of nations. This is what economists sometimes call lock-in, the phenomenon in which an existing system, even an inferior one, persists far longer than a purely technical analysis would predict, because the system has created its own self-perpetuating ecosystem of economic interests, political relationships, and social dependencies. Lock-in is why the internal combustion engine dominated personal transportation for over a century, despite the availability of electric motors since the mid-19th century. It is why coal has remained a major source of electricity in economies where natural gas is substantially cheaper. It is why energy transitions in history have never been sudden replacements, but always slow, multi-decade overlapping transitions in which old sources decline gradually while new ones grow to meet increasing demand. The current energy transition is the largest attempted transition in the history of human civilization. Its scope is genuinely unprecedented, replacing the primary energy substrate of a global industrial system serving 8 billion people on a timescale defined partly by technology, partly by markets, and partly by the growing urgency of climate change. Global energy-related CO2 emissions rose by around 0.4% in 2025, still hitting a new record high of more than 38 billion tons, continuing a pattern in which efficiency gains and renewable deployment are partially offset by growing total energy demand in developing economies. China alone accounted for more than half the global increase in electricity demand in 2024, and about 2/3 of all renewable capacity connected to the grid that year. China's electricity consumption has been growing faster than its economy since 2020, underscoring the speed at which electrification across all sectors is taking hold. But China is also still running roughly 60% of its electricity generation from coal. India, where coal provides nearly 3/4 of electricity supply, is adding renewable capacity at record pace, while simultaneously building new coal plants to serve a population whose per capita energy consumption remains a fraction of that in wealthy nations, and whose legitimate developmental aspirations will drive energy demand sharply upward in coming decades. This tension between the urgent need to decarbonize the energy system and the equally urgent need to extend energy access to the billions of people currently underserved by it is the central political economy of the global energy transition. Around 730 million people remain without electricity, and some 2 billion lack access to clean cooking. Since 2010, 1.5 billion people have gained access to clean cooking and 1 billion to electricity, demonstrating that rapid progress is possible. But the fact that hundreds of millions of people still live without reliable electricity is not merely a humanitarian concern, though it is certainly that. It is also a reminder that the global energy system, as it currently exists, is profoundly unequal. That the 0.73 on the Kardashev scale is an average that masks enormous variation between the energy consumption of a person in Oslo and a person in rural Niger. A genuinely Type 1 civilization would be, by definition, one that had solved this inequality. Not because Kardashev's scale demands equity as a criterion. It doesn't, it measures aggregate power consumption. But because the infrastructure and governance systems required to manage planetary energy at Type 1 scale could not, realistically, coexist with a world in which large fractions of the human population lack access to electricity. Planetary energy management requires planetary participation. You cannot manage a global energy grid from which 1/4 of the human population is effectively excluded. There is, however, a more optimistic reading of the political economy, and it is grounded in the actual trajectory of renewable energy costs over the past 15 years. The cost of solar photovoltaic energy has fallen by more than 90% since 2010. The cost of lithium-ion batteries has fallen by more than 95% since 2008. Onshore wind is now the cheapest source of new electricity generation in most of the world. These cost reductions are not projections or promises. They are empirical facts, measured in auction prices and market transactions. And they have happened faster than virtually every mainstream energy forecast from a decade ago predicted. The mechanism behind these cost reductions is one that economists have studied for decades under various names: Wright's law, the experience curve, learning by doing. For every doubling of cumulative production of a manufactured good, costs tend to fall by a predictable percentage. For solar modules, that percentage has been roughly 20 to 23% for every doubling of cumulative production. Solar capacity has been doubling approximately every 3 years in recent years. If that rate continues, and there are reasons both to expect it might and to expect it might not, the economics of clean energy would become so overwhelming that the political obstacles to adoption would begin to dissolve, not because of policy pressure, but because of simple market logic. Some researchers think this dynamic has already passed a tipping point, that the energy transition is now self-sustaining, driven by economic logic rather than requiring ongoing political subsidization. Others argue that the final 30 or 40% of the decarbonization problem, seasonal storage, industrial heat, long-distance aviation, shipping, steel and cement production, will prove qualitatively harder than the first 60 or 70%, and that market logic alone will not be sufficient to solve it on the timescale that the climate problem requires. Both groups are probably right about something. The first phase of the energy transition, displacing coal and gas from electricity generation in markets where solar and wind can compete head-to-head, is well underway and may indeed be self-sustaining. The second phase, decarbonizing the harder sectors, building the storage and grid infrastructure for a fully renewable system, and extending clean energy access to the billions currently underserved, is harder, slower, and more dependent on policy, international cooperation, and technological innovations that are not yet commercially proven. And the third phase, the phase that would actually begin to move our Kardashev number meaningfully toward 1.0, involves going far beyond decarbonization. It involves not just replacing existing fossil fuel energy with clean alternatives, but multiplying total energy access by factors of 10 or 100, extending that access to every human being on Earth, and building the governance systems that can manage a planetary energy infrastructure at that scale. That third phase is not yet visible on any serious policy agenda anywhere in the world. This is worth staying with, not as a cause for despair, but as a clear-eyed recognition of the scope of what the Kardashev question is actually asking. When people debate our proximity to Type 1, they are almost always debating the first phase, the energy transition currently underway, which is genuinely accelerating and genuinely important. But Type 1 is not the completion of the energy transition. Type 1 is something qualitatively beyond it. Type 1 is a civilization that commands, reliably and sustainably, a power budget roughly 500 times larger than our current one. The energy transition currently underway, if it succeeds fully, would take us from 0.73 to perhaps 0.75 or 0.76 on the Kardashev scale, an enormously consequential achievement for the climate and for human welfare, but a barely perceptible movement toward the Type 1 threshold. That said, there is a phenomenon in complex systems that makes linear extrapolation unreliable over long timescales, and it operates in both directions. Systems can change far more slowly than projections suggest, and they can also, under certain conditions, change far faster. The same cost curves that have driven solar and battery prices down more than 90% in 15 years could, if extended to other technologies, fusion, advanced geothermal, orbital solar, produce further discontinuities that compress the Type 1 timeline in ways that no current model can predict. Pause here, because something here deserves attention. The history of energy transitions suggests that the technologies that ultimately define an era are rarely those that analysts predicted a generation earlier. In 1900, the dominant prediction for the future of electricity was distributed direct current generation. Small generators, localized grids, supplied primarily by coal. Alternating current, the technology that actually enabled the modern grid, had been commercially demonstrated, but was not the consensus favorite. In 1950, nuclear fission was widely expected to become too cheap to meter within a generation. In 1970, solar photovoltaics were an exotic technology used in space applications, too expensive for any commercial terrestrial use. The specific path by which humanity might approach Type 1 is genuinely uncertain, not in the vague hand-waving sense, but in the rigorous sense that the enabling technologies and social configurations that will characterize civilization in 2150 are not yet identifiable from our current vantage point. What we can identify are the necessary conditions, the kinds of things that would need to be true in combination for a trajectory toward Type 1 to be genuine rather than nominal. Clean energy would need to become abundant enough and cheap enough that access expands dramatically rather than merely shifting from one source to another. Storage and grid architecture would need to mature to the point where intermittency is not a fundamental constraint. Political and governance systems would need to develop the capacity for planetary scale coordination that they do not currently possess. And energy access would need to be extended to the entire human population, not as a gift from rich nations to poor ones, but as an infrastructure of mutual benefit in which every region participates. None of these conditions is beyond the reach of human civilization. Each of them is genuinely difficult. The next layer we need to descend through is one that connects the Kardashev question to a body of thought that has grown substantially in recent decades. The question of how the energy transition connects to the specific technologies that some researchers believe could either accelerate our progress toward Type 1 or, in the worst cases, derail it entirely. Technologies that sit at the intersection of enormous promise and genuine existential risk. Technologies that define what it might mean to navigate the adolescence of civilization. The first and most immediate of these is artificial intelligence. Artificial intelligence, in its current form, is primarily an energy consumer. Data centers globally consumed around 180 terawatt-hours of electricity in 2024 in the United States alone, according to IEA estimates. Companies like Meta, Amazon, Alphabet, and Microsoft committed to spend $320 billion on AI and data center infrastructure in 2025, up from $230 billion the previous year. Data center electricity demand is expected to steadily rise through 2030, with consumption projected to increase by approximately 240 terawatt-hours relative to 2024 levels. Wood Mackenzie's modeling suggests that data center expansions could increase the sector's global electricity consumption from 500 terawatt-hours in 2023 to 4,500 terawatt-hours by 2050. This is a large number in the context of current electricity consumption, and it has drawn significant attention from grid planners and policymakers. But in the context of the Kardashev scale, it is worth noting that even the most aggressive projections for AI electricity demand represent a small fraction of the gap between our current position and Type 1. The AI data center build-out at its projected peak would add perhaps a fraction of a terawatt to global primary energy consumption, significant for grid planning, essentially invisible at the Kardashev scale. What AI offers to the Kardashev question is not primarily as an energy consumer, but potentially as an enabling tool, a technology that could accelerate the development and deployment of the clean energy systems, the materials science innovations, and the grid optimization algorithms that the transition requires. Consider materials science. The development of new materials for solar cells, batteries, fusion reactor components, and high-temperature superconductors has historically been slow because the parameter space of possible materials is essentially infinite, and experimental testing of each candidate is time-consuming and expensive. AI-driven materials discovery, of which there are now multiple active research programs at institutions including DeepMind, MIT, and Stanford, offers the possibility of dramatically compressing this timeline by predicting the properties of new materials computationally before they are synthesized experimentally. There are early but genuine results in this direction. AI systems have already identified novel crystal structures and electrolyte compositions that human researchers had not previously explored. Consider grid optimization. The management of a complex electricity grid with high proportions of variable renewable generation requires real-time optimization of supply, demand, storage, dispatch, and transmission routing across enormous numbers of nodes. These are exactly the kinds of large-scale optimization problems at which AI systems excel. Several grid operators in Europe and North America have already deployed machine learning systems for generation forecasting and demand management, with measurable improvements in grid stability and renewable utilization. Consider fusion itself. The plasma physics of fusion confinement involves controlling an enormously complex, high-dimensional physical system in real time. Progress in fusion has historically been limited, not just by engineering challenges, but by the difficulty of developing a deep enough theoretical understanding of plasma behavior to guide experimental design effectively. AI-assisted plasma physics, in which machine learning models are trained on experimental data to predict plasma instabilities and optimize magnetic field configurations, has emerged as a promising research direction, with early results from experiments at MIT's Plasma Science and Fusion Center and at DeepMind's partnership with the Swiss Federal Institute of Technology's tokamak in Lausanne, suggesting that the approach can meaningfully accelerate progress. Some researchers think the combination of AI-accelerated materials discovery, AI-optimized grid management, and AI-assisted plasma physics could compress the timeline to commercially viable fusion by a decade or more relative to trajectories that rely solely on traditional experimental methods. Others are more cautious, noting that the fundamental physics challenges of fusion, sustaining a plasma at temperatures exceeding 100 million degrees while confining it with magnetic fields, and doing so reliably enough and cheaply enough to power a commercial electricity grid, are not primarily problems of data analysis or optimization, but of fundamental engineering at extreme conditions that no algorithm can bypass. What is genuinely new in the current moment is the convergence of multiple accelerating technologies in a way that creates genuine uncertainty about the rate of progress. 10 years ago, the question of when fusion might be commercially viable had a fairly clear consensus answer among experts. not within this century with high probability. That consensus has shifted. It has not shifted to fusion is imminent. Most serious researchers still place commercial fusion several decades away at an optimistic minimum. But it has shifted enough that fusion within the lifetime of someone born today is now a defensible claim rather than a fantasy. And that shift matters for the Kardashev question, because the timeline to Type 1 is not fixed. It is a function of what technologies we develop, how quickly we deploy them, and what social and political decisions we make in the decades ahead. The lower bound on the Type 1 timeline, the fastest plausible path, is genuinely uncertain, and it has become somewhat less certain in recent years as technologies that were once firmly in the speculative category have moved into the domain of active engineering. Here is what that means in concrete terms. Under what might be called a fast transition scenario, one in which solar costs continue their current decline, fusion achieves commercial viability by 2060, AI materially accelerates both materials science and grid optimization, and political coordination improves sufficiently to enable planetary-scale energy infrastructure deployment. Our Kardashev value might reach something like 0.8 or 0.85 by the end of this century. That would represent genuine and remarkable progress. It would represent a civilization that has largely decarbonized, extended clean energy access to most of the global population, and begun to deploy energy infrastructure at scales previously unimaginable. Under more conservative assumptions, fusion delayed, political fragmentation worsening, energy access expanding slowly. The 2100 Kardashev value might be closer to 0.76 or 0.77. Still progress. Still a cleaner, more electrified world than the one we have today, but barely visible movement toward the Type 1 threshold. In both scenarios, Type 1, in the full physically meaningful sense of genuine planetary energy mastery, remains comfortably beyond the horizon of this century. The question of whether it lies within the horizon of the next century or the century after that depends on decisions and discoveries not yet made. Some researchers think the most important variable is not any specific technology, but the question of whether human civilization develops the institutional capacity for the kind of long-range planetary-scale coordination that the Type 1 project requires. Michio Kaku, writing about the Kardashev transition, has suggested that the primary obstacle is not energy technology, but governance. The construction of planetary institutions capable of managing a shared energy infrastructure without the fragmentation and conflict that currently characterize international relations. Others think this frames the problem incorrectly. They argue that sufficiently cheap, abundant, and decentralized energy, a world in which solar and storage are so inexpensive that almost any actor can deploy them at scale without centralized coordination, could actually enable Type 1 approaching energy consumption without requiring anything like a world government or global energy authority. If the technology becomes cheap enough, the economics drive adoption bottom-up without needing top-down coordination to force it. Both arguments contain genuine insight, and they are not necessarily in conflict. The decarbonization and energy expansion aspects of the Type 1 transition might proceed bottom-up, driven by economics. The planetary management aspects, coordinating the atmospheric effects of large-scale energy infrastructure, managing the geopolitical implications of a world in which some nations have achieved energy abundance and others have not, governing the use of technologies like geoengineering that affect the entire planetary system regardless of national borders. Those aspects may require coordination mechanisms that have no historical precedent. That is where we now go. into the civilizational dimension of the Kardashev question, the dimension that sits not in physics or engineering, but in human nature, in the structure of our political institutions, in the long and complicated history of how our species has managed or failed to manage shared resources at increasing scales of complexity. Because here is what the scale quietly implies, beneath all the numbers and watts and terawatts. A Type 1 civilization is not just a civilization that has more energy. It is a civilization that has become something qualitatively different. A civilization that has, in some meaningful sense, grown up. And the question of whether that transition is achievable is, at its deepest level, not a question about solar panels or fusion reactors. It is a question about us. Now hold two thoughts simultaneously. The first, those lights on the horizon represent an achievement so staggering in its complexity that no individual human mind can fully comprehend it. A modern city is a system of systems: electrical, thermal, hydraulic, logistical, computational, biological, operating continuously, in parallel, at scales that would have been regarded as miracles by any civilization in history before roughly 1880. The fact that you can flip a switch and receive light, that you can open a tap and receive clean water, that food arrives daily from across the continent and around the world in quantities sufficient to feed millions of people. These things are the product of institutions, technologies, and social agreements so intricate and interdependent that their failure modes are still not fully understood by anyone. The second thought. From the perspective of the Kardashev scale, those lights represent a civilization that has, so far, managed to harness approximately 1/10,000th of the energy available to it on its own planet. A civilization still burning its geological inheritance to heat its buildings. A civilization that has split the atom but cannot yet sustain fusion. A civilization of 8 billion people divided into 200 competing political units, many of whom cannot agree on the basic facts of the physical world they share. Both thoughts are true. The gap between them is where the most interesting thinking about our future lives comes from. Now we descend into the layer of this story that most directly addresses that gap. Not the layer of physics or engineering, but the layer of civilizational coordination, historical precedent, and the sociology of how complex societies have, or have not, managed to organize themselves around shared challenges at increasing scales of complexity. Because the obstacles between us and Type 1 are not primarily technical, they are structural. And understanding the structure of those obstacles requires looking carefully at how we have handled comparable challenges in the past. The history of human coordination is, in one reading, a history of expanding circles. The earliest human groups were small, bands of 20 to 50 individuals, coordinating through direct social relationships, managing shared resources through norms enforced by the visible social fabric of the group. As populations grew and agricultural surpluses accumulated, those bands aggregated into villages, then into chiefdoms, then into early states. Each expansion of the coordination circle required new institutional technologies: writing, law, currency, bureaucracy, religion, to manage relationships between people who could no longer know each other personally. The nation-state, which has served as the dominant organizational unit of human civilization for roughly 300 years, represents one of the most powerful coordination technologies ever invented. It solved the problem of coordinating tens or hundreds of millions of people around shared infrastructure, shared defense, shared currency, and shared law with a robustness and scalability that earlier organizational forms could not match. The nation-state, combined with the industrial economy, created the energy infrastructure we now have, and created it with remarkable speed. The electrical grid of the United States, which now spans a continent and serves hundreds of millions of people, was built from essentially nothing in roughly 60 years between the late 1880s and the late 1940s. But the nation-state, precisely because of its success, has created its own lock-in problem at the planetary scale. The challenges that define our current civilizational moment: climate change, pandemic preparedness, nuclear proliferation, the governance of artificial intelligence, and yes, the energy transition required for Type 1, are all challenges that do not respect national borders. They are, in the precise technical sense, global commons problems. A global commons problem is one in which the resource or system in question is shared by all actors, but the costs and benefits of individual actions are distributed unevenly, creating structural incentives for each actor to defect from cooperative solutions in pursuit of narrow short-term self-interest. Climate change is the canonical example. The atmosphere is a shared resource. The cost of emitting carbon dioxide is distributed globally and across generations, while the benefit, the cheap energy from burning fossil fuels, accrues locally and immediately. No individual nation, acting alone, has sufficient incentive to bear the full cost of decarbonization, because a nation that unilaterally accepts high energy costs, while others do not, simply disadvantages itself economically without meaningfully reducing global emissions. The rational strategy for each individual actor in the absence of binding global coordination is to emit as much as is locally beneficial while hoping that others bear the costs of restraint. This is not a novel observation. It is the fundamental logic of every global commons problem, and it was articulated with formal precision by the ecologist Garrett Hardin in 1968 in his paper The Tragedy of the Commons, published in the journal Science. Hardin's analysis suggested that shared resources would inevitably be depleted by rational individual actors in the absence of enforced collective rules. The political scientist Elinor Ostrom, who received the Nobel Prize in Economics in 2009, spent much of her career demonstrating that Hardin's pessimistic conclusion was not inevitable, that human communities had, repeatedly and in diverse cultural contexts, developed institutional arrangements that allowed shared resources to be managed sustainably without either privatization or top-down state control. Ostrom's 1990 book, Governing the Commons, documented dozens of case studies, from Swiss alpine meadows to Japanese fishing villages to Spanish irrigation systems, in which local communities had self-organized around sophisticated rules for managing shared resources across generations. Ostrom's findings are genuinely hopeful. They suggest that the structural logic of the commons problem does not inexorably lead to tragedy, that human societies are capable of developing the institutions, norms, and enforcement mechanisms necessary to manage shared resources, well, given sufficient time, trust, and repeated interaction. But they also reveal something important about the scale requirements for successful commons governance. In every case Ostrom studied, the commons was bounded. It had a defined community of users, a resource whose state could be monitored, and a set of rules whose violations could be detected and sanctioned by community members who interacted repeatedly with one another. The atmosphere, the global climate system, the governance of planetary energy infrastructure. These are commons problems at scales that dwarf anything Ostrom's case studies addressed. The community of users is every human being on Earth. The resource, stable atmospheric chemistry, equitable energy access, a livable climate, cannot be easily monitored in ways that attribute specific costs to specific actors. And the enforcement of any cooperative agreement requires mechanisms that transcend national sovereignty in ways that most governments regard as politically unacceptable. This is the governance gap, the distance between the institutional capacity we have and the institutional capacity that Type 1 would require. And it is, arguably, the single largest obstacle between us and that first rung of the Kardashev ladder, larger, in the long run, than any technical challenge, more difficult to solve, in the sense that solving it requires changes to human political culture and institutional design that have no simple engineering analog. Some researchers think that artificial intelligence, by creating shared dependencies and shared risks at a speed that forces institutional adaptation, might actually accelerate the development of global governance capacity. The argument is that when sufficiently powerful actors face the same AI-related risks, misaligned AI systems, autonomous weapons, economic displacement at scale, the political incentives for international coordination will strengthen in ways that currently seem unlikely. Others argue that AI, by empowering individual actors with unprecedented capabilities, will actually accelerate fragmentation, making it easier for small groups to act with consequences that previously required state-level resources, and harder for any coordinating institution to establish and maintain meaningful authority. Both of these scenarios are live possibilities. We genuinely do not know which way the next century of governance development will move. What history does tell us is that major expansions in the scope of human coordination have, in the past, tended to happen under pressure, when the consequences of failing to coordinate became severe enough that the political costs of building new institutions became lower than the costs of not building them. The institutional architecture of the post-World War II period, the United Nations, the International Monetary Fund, the World Bank, the General Agreement on Tariffs and Trade, was built in the shadow of the most destructive conflict in human history, precisely because the experience of that destruction had created the political conditions for institutional innovation that would have been impossible in less extreme circumstances. The question is whether the pressure of climate change, energy insecurity, and technological disruption is, or will become, sufficient to create analogous political conditions for the institutional innovation that the Type 1 project requires. Some researchers argue that the window for this kind of voluntary institutional transformation is closing, as political fragmentation and distrust between major powers deepens. Others argue that the very scale of the challenges we face will eventually force a kind of civilizational reckoning that produces the needed innovations, however painfully and slowly. This is worth pausing on, because it represents a genuine epistemological limit, not merely a gap in our current knowledge, but a question whose answer depends on choices not yet made by people not yet born. We cannot know whether human civilization will develop the institutional capacity for planetary coordination. We can only trace the logic of the problem, examine the historical precedents, identify the conditions that have historically enabled or disabled large-scale coordination, and acknowledge that the outcome is, in the most honest sense, undetermined. What we can say with confidence is this: the energy transition currently underway, even if it proceeds at its most optimistic projected pace, does not solve the governance problem. A world that runs on clean energy but remains politically fragmented, institutionally weak at the planetary scale, and incapable of managing shared atmospheric and ecological systems as a common resource, is a world that has made important progress but has not achieved anything resembling Type 1. The energy number might improve. The civilizational maturity required to sustain and manage that energy number would still be absent. And here is where the Kardashev scale begins to reveal something that goes considerably deeper than a measurement of power consumption. Something about the relationship between energy and civilization that Kardashev himself may not have fully articulated when he first drew his ladder in 1964. Energy is not just fuel, it is the substrate of complexity. Complex systems, biological, social, technological, require continuous energy inputs to maintain themselves against entropy. A living cell uses energy to maintain the chemical gradients that define its internal order. An ecosystem uses energy to sustain the network of relationships between species that constitutes its structure. A city uses energy to maintain the flow of goods, information, and people that constitutes its function. A civilization uses energy to sustain the institutional and technological infrastructure that constitutes its capacity to act in the world. This relationship between energy and complexity was formalized by the physicist and cosmologist Eric Chesson, who has spent several decades developing what he calls cosmic evolution, a framework for understanding the progression from simple physical systems to complex organized ones in terms of their energy rate density, measured in watts per kilogram of system mass. Chesson's work, developed across multiple books and papers from the 1980s onward, suggests that the complexity of a system correlates with the rate at which it processes energy per unit mass. A star processes energy at a rate of roughly 2 watts per kilogram of stellar material. A bacterial cell processes energy at something like 1,000 watts per kilogram. A human brain, which accounts for about 2% of body mass but consumes roughly 20% of resting metabolic energy, processes energy at something on the order of 15,000 watts per kilogram of brain tissue. A modern city, with its continuous flows of electricity, thermal energy, chemical energy in food and fuel, and information, has an energy rate density that, per unit mass of the system's physical infrastructure, is many times higher than that of a human body. What Chesson's framework suggests is that the Kardashev scale is not merely measuring a quantity, the total power consumption of a civilization, but is, in effect, tracking the complexity of civilization itself. As a civilization commands more energy per unit of its structural mass, it becomes capable of maintaining higher levels of organized complexity, more sophisticated institutions, more intricate technology, more subtle forms of social coordination, more powerful capabilities for managing and transforming its environment. This reframing has a deeply important implication for the question at the center of our exploration. If energy and complexity are coupled in the way Chesson's framework suggests, then the path to Type 1 is not simply a path of building more power plants. It is a path of becoming more complex, more organized, more internally differentiated, more capable of coordinating across scale. And the limits on that path are not primarily limits of physical resource availability. They are limits of organizational capacity, of institutional maturity, of the ability to maintain coherent collective action across the full span of a species. Here is something that almost nobody considers when they talk about the Kardashev scale. The transition from Type 0 to Type 1 may be less like a technological achievement and more like a developmental one, less like building a bigger engine and more like reaching adulthood. And reaching adulthood, for a civilization as for an individual, is not primarily a matter of accumulating more resources. It is a matter of developing the internal structures, the judgment, the self-restraint, the capacity to defer immediate gratification in service of longer-term flourishing, that allow those resources to be used wisely rather than destructively. The transition from Type 0 to Type 1 is considered the most dangerous period in a civilization's development. Not dangerous because the technology is difficult. Dangerous because the combination of enormous and growing power, nuclear weapons, biotechnology, artificial intelligence, with insufficient wisdom to wield it, creates conditions in which civilizational self-destruction becomes a live possibility rather than a theoretical one. We are, in Kardashev's framework, adolescents with access to tools that require adult judgment. And the history of adolescence, at both the individual and the civilizational scale, suggests that the transition to maturity is neither guaranteed nor painless. This brings us to the part of the Kardashev question that most directly connects to the oldest and strangest question in all of science: the Fermi paradox. If Type 1 civilizations are achievable, and if the universe is as old and as large as we know it to be, approximately 13.8 billion years old, containing something on the order of 2 trillion galaxies, each containing hundreds of billions of stars, a substantial fraction of which have planets in habitable zones, then the universe should, on even conservative estimates, contain enormous numbers of civilizations far more advanced than our own. The Italian-American physicist Enrico Fermi, lunching with colleagues at Los Alamos National Laboratory in New Mexico in 1950, posed the question that has haunted SETI research ever since. Where is everybody? Where are the Type 2 civilizations whose Dyson spheres should be visible as infrared anomalies across thousands of light years? Where are the Type 3 civilizations whose restructuring of galactic energy flows should be detectable at cosmological distances? The universe is not merely silent. It is deeply, almost provocatively silent. The search for extraterrestrial intelligence has been scanning the skies in multiple wavelengths for more than 6 decades, and the only signal that even briefly resembled something artificial, the famous "wow" signal detected by astronomer Jerry Eman at Ohio State University's Big Ear Radio Telescope in Delaware, Ohio, on August 15, 1977, was a single brief pulse that has never been repeated or explained. The absence of detected signals from advanced civilizations is not proof that they do not exist. It could reflect the limits of our search technology, the possibility that advanced civilizations communicate by methods we have not thought to look for, the sheer scale of the universe, and the challenge of detecting any signal across interstellar distances, or any number of other explanations that preserve the possibility of a universe teeming with life. Some researchers think the apparent absence is simply a function of the fact that we have searched a tiny fraction of the parameter space of possible signals, using instruments that would not detect our own civilization's radio emissions from even a few light years away. But the Fermi paradox also connects uncomfortably to the Kardashev question in a way that deserves careful consideration. Because one possible explanation for the silence, not the only explanation, but a logically coherent one that several serious researchers have taken seriously, is what the economist and social scientist Robin Hanson called the Great Filter in a 1998 essay. The Great Filter hypothesis suggests that somewhere along the developmental path from simple chemistry to interstellar civilization, there exists a barrier, a transition so difficult, so unlikely, or so dangerous that almost no civilization successfully navigates it. If the Great Filter lies behind us, if the hardest step is the one from non-life to life, or from simple to complex cells, or from complex cells to multicellular organisms, then we are potentially among the lucky few who have made it past the filter, and the path to Type 1 and beyond is, in principle, open. But if the Great Filter lies ahead, if it is precisely the transition that we are currently attempting, the navigation of adolescence with world-ending technology, then the silence of the universe begins to look like a warning rather than an absence of evidence. The great filter, if it lies ahead, does not announce itself. It looks like the normal trajectory of a civilization approaching its peak of complexity and capability, right up until the moment when something goes irreversibly wrong. It could look like a civilization that develops artificial general intelligence before developing the wisdom to align it with human values. It could look like a civilization that develops engineered pathogens with pandemic potential that exceed its ability to respond. It could look like a civilization that, having built the physical infrastructure of Type 1 energy, fragments politically and uses that infrastructure as a weapon rather than a commons. It could, conceivably, look like us. This is not a prediction. It is a possibility space. And acknowledging that possibility space is not pessimism. It is the honest intellectual work of taking the Fermi paradox seriously as a data point about the developmental trajectories of technological civilizations. The Kardashev scale, viewed through the lens of the Fermi paradox, becomes something more than a measurement of energy consumption. It becomes a map of a developmental journey that may have a narrow passage somewhere in it, a passage through which many civilizations do not emerge, and through which no civilization yet known to us has ever emerged into the fully realized state that Type 1 represents. Take stock of where we are. We have descended through the full architecture of the problem, layer by layer. We began with the number 0.73 and unpacked what it means, where it comes from, and what the gap between it and 1.0 actually requires. We have examined the physics of the energy system we have built, the pace of the transition currently underway, the material and thermodynamic constraints that shape its limits. We have looked at the governance challenges, the coordination problem at planetary scale, the tragedy of the commons, the Ostrom framework and its limitations when extended to global scope. We have descended into the relationship between energy and complexity, and the possibility that Type 1 is less a technical milestone than a developmental one. And we have arrived, finally, at the most unsettling dimension of the question, the possibility that the silence of the universe is not an absence of data, but a kind of message. Now we go somewhere different, quieter, more difficult. We go to the question that the Kardashev scale does not ask, but that it implies with every digit of its measuring. What would it mean to actually get there? Not in the technical sense, not in the governance sense, in the deepest sense, the sense that asks what kind of species, what kind of civilization, what kind of collective consciousness would be capable of genuinely mastering the energy of an entire planet while remaining, in any meaningful sense, recognizably human. Because here is the question that sits beneath all the others, and that no engineering roadmap and no policy framework can fully address. Type 1 requires managing planetary systems, atmospheric chemistry, ocean circulation, the hydrological cycle, weather patterns, the distribution of heat across continents and oceans. These are systems of staggering complexity, involving feedback loops and tipping points that our best models can approximate but not fully capture. Managing them deliberately, not just influencing them accidentally, as we currently do through carbon emissions, but managing them intentionally, as a Type 1 civilization would need to do, requires not just more computational power, or more sensors, or more sophisticated algorithms. It requires a degree of collective judgment and shared values that transcends anything our current political culture can reliably produce. Consider one specific example: geoengineering, stratospheric aerosol injection, the deliberate release of reflective particles into the upper atmosphere to reduce solar insolation and counteract global warming. is a technology that is, in principle, available right now. The physics are reasonably well understood. The costs are not prohibitive. A nation-state with sufficient will and resources could unilaterally begin altering the global climate within years. The consequences of doing so, the effects on regional precipitation patterns, on agriculture across dozens of nations, on the monsoon systems that water the crops of billions of people, would be distributed globally and unevenly, with some regions benefiting and others suffering. The governance problem this creates is among the most complex in the entire portfolio of planetary management challenges. Some researchers think stratospheric aerosol injection should be studied seriously as a potential emergency measure if climate change accelerates beyond manageable thresholds. Others argue that even studying it creates a moral hazard, reducing the pressure to decarbonize by offering the illusion of a technological escape valve, and that any actual deployment, absent global governance frameworks that do not currently exist, would be an act of unilateral planetary modification with potentially catastrophic consequences for nations that did not consent to it. Both camps have real arguments, and the impossibility of fully resolving this debate, of finding a governance framework that commands sufficient global legitimacy to manage stratospheric aerosol injection responsibly, illustrates, in miniature, the full scope of the governance challenge that Type 1 implies. A Type 1 civilization would need to make decisions like this routinely, across dozens of planetary systems simultaneously, over timescales of decades and centuries. It would need to do so with sufficient legitimacy that its decisions commanded broad compliance, with sufficient wisdom that its interventions did not produce worse outcomes than the problems they were intended to solve, and with sufficient flexibility that it could adapt as new information emerged. This is not a description of any governance system that has ever existed. It is a description of something that would need to be invented, not just designed on paper, but actually built and tested and refined through the long, difficult, failure-prone process by which all institutions are actually forged. And forged is the right word, not constructed, not designed, forged, under pressure, over time, through conflict and compromise and iteration, in ways that cannot be fully planned in advance. This is the deepest implication of the Kardashev question, and it is the one that tends to get lost in the excitement of the technical roadmaps and the energy projections and the fusion timelines. The question of how close we are to Type 1 is not ultimately a question about watts. It is a question about wisdom. And wisdom, unlike watts, does not scale with infrastructure investment or accumulate on an exponential cost curve. Wisdom accumulates slowly through the hard experience of failure and consequence, through the long work of building institutions that embody collective judgment, through the painstaking construction of shared narratives that allow large groups of people to act together in the face of uncertainty and disagreement. We have some of it, more than our most despairing moments suggest. The fact that we have not yet used nuclear weapons in warfare since 1945, despite the existence of thousands of them, despite multiple crises in which their use came close to happening, is, in the context of human history, a remarkable achievement of collective restraint. The fact that the ozone layer is recovering following the 1987 Montreal Protocol, in which the nations of the world successfully coordinated to ban a class of industrial chemicals that were destroying the atmospheric shield that protects life on Earth, is an example of exactly the kind of planetary commons governance that Type 1 implies. And it worked. The ozone hole, which was catastrophically expanding in the 1980s, began leveling off around 2000 and has shown measurable recovery since then, though full Antarctic recovery is projected only around 2066, and global recovery to pre-1980 levels is expected around 2040. The Montreal Protocol was not perfect. It was slow in some respects, incomplete in others, and required ongoing revision as new threats were identified. But it demonstrated in practice that international coordination around shared planetary systems is possible, that the governance gap, while real, is not absolute. That matters. It matters because the path to Type 1, if there is a path, runs through dozens of Montreal protocols, dozens of institutional innovations, each addressing a specific shared challenge at the planetary scale, each building incrementally on the trust and precedent established by the ones before it. Now we are ready to enter the part of this exploration that changes the shape of everything we have learned. The intellectual mountain we have been climbing, the terrain of physics and engineering and governance and evolutionary dynamics, has a ridge at its top, and from that ridge, the view is different. It reveals something about the Kardashev scale that the scale itself does not explicitly state, something that only becomes visible when you have climbed far enough to see the full landscape. It is this. The question, how close are we to Type 1, is not only a question about the future. It is a question about the present, about what we are doing right now in this decade and this century that will either open or close the pathways by which Type 1 becomes achievable. The decisions made in the next 50 years about energy infrastructure, about governance, about AI development, about international cooperation, about the distribution of economic benefits, will shape the trajectory of human civilization for centuries. Not because those decisions are uniquely powerful in some mystical sense, but because we are, by the evidence of physics and history, at a genuine inflection point. The adolescence metaphor has been used twice in this story, and it is worth returning to it one more time, because it carries more weight than it might initially seem. An adolescent is not simply an immature adult. An adolescent is a system in transition, a system that has outgrown the institutional forms that served it in childhood, and has not yet developed the institutional forms that will serve it in adulthood. The instability of adolescence is not a flaw in development. It is a necessary feature of a transition between two qualitatively different modes of operating. The dangerous part is not the instability itself, but the combination of adolescent power with insufficient adult structure. We have, as a species, enormous power. The power to alter the climate, the power to engineer biology, the power to build and operate nuclear arsenals capable of ending civilization, the power to create artificial intelligences that may, within decades, exceed human cognitive capability across multiple domains. And we have institutions that were designed for a different world, a world of separate nations, separate economies, separate information environments that are struggling, visibly and in real time, to keep pace with the capabilities they are being asked to govern. This is not a unique historical situation. It has structural similarities to other moments of institutional lag, moments when the tools available to civilization outpaced the wisdom and governance structures needed to use them well. The development of nuclear weapons in the 1940s, the development of industrial chemistry in the late 19th century, which created both the fertilizers that feed billions and the chemical weapons used in the trenches of the First World War from the same underlying science. The development of the Joint Stock Corporation in the 17th century, which created the machinery of global capitalism, and with it, eventually, the conditions for both the Industrial Revolution and the colonial extraction that funded it. In each case, the lag between capability and governance was resolved not instantly, but over time, through conflict, through catastrophe, through slow institutional adaptation. The nuclear case has not been fully resolved even now. But none of these lags ended civilization. Humanity navigated them at cost and emerged with somewhat more robust institutions than it had before. The question for the Kardashev transition is whether the same pattern holds, whether the governance lag we are currently experiencing between our energy and AI and biotechnology capabilities and our institutional capacity to manage them will resolve, as it has before, through painful but ultimately successful adaptation. Some researchers think this pattern is reliable, that human civilization has a demonstrated capacity for institutional adaptation in the face of existential pressure, and that the Kardashev transition, however difficult, is within the range of challenges that this capacity can handle. Others point to the genuinely novel features of the current situation: the speed of technological change, the scale of the commons problems, the global interconnectedness that means failures propagate faster and farther than they did in previous eras, and argue that there is no historical precedent for what we are attempting, and therefore no guarantee that the historical pattern of successful adaptation will repeat. We cannot know. That is the honest answer. We cannot know whether the institutions and the wisdom required for Type 1 are within the developmental reach of our species, because those institutions and that wisdom do not yet exist, and their creation depends on choices not yet made. What we can do, what the Kardashev scale at its best invites us to do, is hold the question seriously, not as a source of anxiety or despair, but as a genuine intellectual and moral challenge. The question of what kind of civilization we need to become in order to deserve the title Type 1 is one of the most important questions our species has ever faced. And the fact that it does not have a simple engineering answer, that it requires the harder, slower, less tractable work of civilizational self-examination, does not make it less important. It makes it more important. And now, from this height, from the ridge where the full landscape is visible, we are ready for the view that changes everything. Because there is something about the Kardashev scale that has been present in everything we have discussed, but that has not yet been stated directly. Something that, once you see it, reorganizes the whole picture. Something that turns the scale from a measurement of how far we have come into a mirror that reflects who we currently are, with a clarity that is both humbling and, in a strange way, deeply hopeful. Here is what it is. The Kardashev scale measures energy consumption. But energy consumption in the context of a civilization is a proxy for something else. Something that the physicist David Deutsch, in his 2011 book, The Beginning of Infinity, called the reach of explanatory knowledge. Deutsch argues that the fundamental differentiating characteristic of civilizations is not their energy budget, not their population size, not their military power, but their capacity to generate and apply knowledge that allows them to solve problems, including problems they have never encountered before. By this measure, the distance from Type 0 to Type 1 is not primarily a distance measured in watts. It is a distance measured in knowledge, in the depth, breadth, and reliability of the understanding that a civilization has of its own physical, biological, and social systems, and in the institutional structures that allow that understanding to be translated into effective collective action. And here is the reframe that reorganizes everything. By the measure of knowledge, by the measure of explanatory reach, of the ability to understand and engage with novel problems, of the capacity for rational collective self-examination, the progress humanity has made in the past 3 centuries is not the modest increment from 0.70 to 0.73 that the energy numbers suggest. It is something far more dramatic. In the past 3 centuries, humanity has gone from a species that did not know what electricity was, did not know that diseases were caused by microorganisms, did not know that the Earth orbited the Sun, did not know that the universe was older than 6,000 years, to a species that has mapped the genome, detected gravitational waves from colliding black holes, built machines that can predict protein structures with near-atomic precision, and is now seriously engineering the first fusion reactors. That knowledge revolution is not reflected in the Kardashev number, because the Kardashev number measures only the energy we are currently using, not the energy we will be able to use once the knowledge we have recently acquired is fully deployed. The number is, in a sense, a lagging indicator, a measure of past infrastructure rather than present capability. And this is where the scale's apparent simplicity collapses into something far more interesting. What would happen to the Kardashev number if humanity deployed over the next century even a fraction of the clean energy potential that its current scientific understanding already describes as physically achievable? If fusion works, and the physics says it can, and if orbital solar energy becomes economically viable, and if the cost curves of terrestrial solar and storage continue their recent trajectories, and if the governance structures required to manage planetary energy infrastructure are built slowly and painfully through the same process by which all enduring institutions are built, then the question is not whether humanity can reach Type 1. It is only a question of when and at what cost and along which path. But here is the thing that almost nobody says explicitly. We cannot know whether fusion will work at commercial scale. We cannot know whether the governance structures required for Type 1 will be built. We cannot know whether artificial intelligence will amplify human wisdom or undermine it. We cannot know whether the current period of political fragmentation is a temporary phase of the institutional lag that always precedes major coordination upgrades, or whether it represents a more durable fracture in the civilizational project. These are not merely gaps in our current knowledge. They are, in the deepest sense, genuinely open questions. Questions whose answers are not determined by the physics of the situation, but by the choices that will be made by humans who are not yet born, in circumstances that do not yet exist, under pressures that we cannot fully anticipate. That indeterminacy is not a failure of the analysis. It is the most important finding of the analysis. The distance between us and Type 1 is not primarily a fixed quantity. It is a variable. It is a variable that depends on what we do, on whether we build the institutions, develop the technologies, accumulate the wisdom, and extend the cooperation that the transition requires. The Kardashev number 0.73 is not a sentence. It is a description of a moment. It is a snapshot of where a civilization stands on a particular Tuesday in the early 21st century, before the choices that will define the next few centuries have been made. What are those choices? What are the specific decisions in the next 50 years that will determine whether the Type 1 transition accelerates or stalls? There are 5 of them that rise above the noise. The first is the fusion question. Will the investments currently being made in ITER and in the growing ecosystem of private fusion companies, including Commonwealth Fusion Systems in Cambridge, Massachusetts, TAE Technologies in California, and Helion Energy in Washington State, among others, result in commercial fusion power by mid-century? If they do, the energy constraint on Type 1 essentially dissolves. The path becomes, fundamentally, a governance and deployment problem rather than a physics problem. If they do not, if fusion continues to slip beyond the horizon, then the path to Type 1 is longer and harder, requiring a renewables and storage build-out of a scale and speed that will test the material and organizational limits of our civilization. The second is the AI alignment question. Will artificial intelligence develop in ways that amplify human collective intelligence and coordination capacity, or in ways that fragment and undermine it? This question is not merely technical. It is the question of whether one of the most powerful tools ever created by our species will serve as a vehicle for the civilizational maturity that Type 1 requires, or whether it will amplify the adolescent instabilities that the transition needs to transcend. The third is the energy access question. Will the clean energy transition be managed in a way that extends genuine energy abundance to the billions of people currently underserved? Or will it reproduce and entrench existing inequalities in new technological forms? A world in which wealthy nations achieve clean energy abundance while developing nations remain energy poor is not a world trending toward Type 1. It is a world trending toward the fractures that make Type 1 governance impossible. The fourth is the institutional question. Will the period of geopolitical stress and institutional fragmentation that characterizes the early 21st century prove temporary, a difficult but navigable passage through institutional lag, comparable in structure to historical transitions that were ultimately resolved? Or will it represent a more fundamental fracture in the capacity for global coordination? The answer to this question is not determined by physics or economics. It is determined by politics, which is to say by the accumulated choices of billions of human beings across decades. The fifth is what might be called the meaning question, the question that the Kardashev scale does not ask, but that Type 1 civilization forces into view. What is all this energy for? What kind of life? What kind of human flourishing? What kind of relationship between civilization and the natural systems that sustain it should a Type 1 civilization embody? Because a civilization that reaches the energy consumption levels of Type 1 while remaining as ecologically destructive, as institutionally fragile, and as morally incoherent as our current civilization would not represent genuine advancement. It would represent a more powerful version of the same adolescent, more capable of destruction, not more capable of wisdom. These 5 questions do not have answers today. They are the questions whose answers will be written by the civilization that exists over the next 100 to 200 years. They are, in the truest sense, ours to answer. Stand somewhere quiet for a moment, not literally. Though if you have found a quiet place to rest while this story unfolds around you, that is exactly right. Stand somewhere quiet inside yourself. Let the accumulated weight of everything we have covered, the numbers, the physics, the governance challenges, the existential uncertainties, settle. Let it come to rest, the way sediment settles in still water, finding its level. Because what we are about to do is something different from everything that has come before. We are not going to add more evidence to the pile. We are not going to introduce another layer of technical complexity or another dimension of civilizational challenge. We are going to do something simpler and, in its own way, harder. We are going to look at what all of this means, not as a calculation, not as a forecast, but as an experience, as something felt rather than merely understood. The intellectual mountain we have been climbing together has a summit of sorts, and it is not a summit that looks like a conclusion. It looks more like a clearing, a place where the trees thin out and the sky opens up, and you can see for the first time the full shape of the terrain you have been moving through. Here is the shape of that terrain. We are a species that emerged from the same stellar processes that forged every atom in our bodies. The carbon in your hands, the oxygen in your lungs, the iron that carries oxygen through your blood. These were made in the cores of stars that died before the sun existed. scattered across space in the violence of supernova explosions, gathered by gravity into the disk of dust and gas that became our solar system, concentrated by geological and biological processes over 4 billion years into the form you currently inhabit. You are, in a very precise and non-metaphorical sense, a way that the universe has organized itself to become aware of its own existence. And you are, at this particular moment in the history of that self-awareness, a member of a civilization that has placed itself on a scale and found its number, 0.73. The scale was invented to classify alien civilizations from a distance. It was meant to tell us what to listen for, what energy signatures to expect from intelligences more advanced than our own. In the 60 years since Kardashev first proposed it, it has become something else as well, a mirror, a way of seeing ourselves from the outside, from the perspective of the cosmos, stripped of the comfortable narratives we tell about progress and destiny and our special place in the order of things. And what the mirror shows is this: we are extraordinary. The complexity of what we have built, the cities, the grids, the hospitals, the communication networks, the scientific institutions, the artistic traditions, the accumulated libraries of knowledge that allow a child born today to access the distilled wisdom of 5,000 years of human thought, is genuinely staggering. By any measure available to us, no other known species in this universe has come close to what we have achieved in the roughly 10,000 years since we first began to plant seeds in soil and call the resulting patch of ground a farm. And we are, by the same mirror's measurement, profoundly incomplete. We are a civilization that has mastered the manipulation of subatomic particles, but not the management of a shared atmosphere. A civilization that has built machines capable of generating more text in a second than a human can read in a lifetime, but has not yet built institutions capable of making collective decisions about how to use those machines wisely. A civilization that has decoded the genome of every major species on Earth, but cannot reliably feed every member of its own. The 0.73 is not an insult. It is a description. It is a description of a civilization that is genuinely, in the most precise available sense, not yet grown up, that has the capabilities of an adult, but not yet the full institutional and moral framework of one. Something here deserves to be held with great care, because the instinctive response to this description for many people is either defensive dismissal or despair. Either, we're doing fine, the doomsayers are wrong, look at how far we've come, or we're doomed, the problems are too large, nothing we do will matter. Both of these responses are understandable. Neither of them is adequate to the situation. The adequate response is something harder and more interesting. It is the response of someone who has looked honestly at a difficult truth and found in that honesty something that feels less like despair and more like orientation, less like a verdict and more like a map, less like an ending and more like a clarification of what the work actually is. What is the work? The work is exactly what it looks like: building the institutions, deploying the technologies, extending the access, developing the wisdom, making the choices, individually, collectively, politically, scientifically, that move the number from 0.73 towards something that genuinely deserves the designation of planetary civilization. Not because a Soviet astronomer drew a line there in 1964 and we want to cross it, but because what lies on the other side of that line, a civilization capable of managing its planetary systems sustainably, of extending genuine abundance to all its members, of wielding the enormous power it has accumulated with something approaching wisdom, is worth becoming. And here is where the story takes a turn that is not expected. The most hopeful thing about our current position is not the rate of solar panel installation, or the progress of fusion research, or the growth of international institutions, or any other specific data point about the energy transition currently underway. The most hopeful thing is that we are asking the question. The fact that the Kardashev scale exists, that a scientist in the Soviet Union in 1964, in the middle of a Cold War that brought humanity within hours of nuclear catastrophe on multiple occasions, sat down and thought carefully about what an advanced civilization would look like, and created a framework that allows a species to measure its own civilizational maturity, is itself a form of the kind of reflective self-awareness that Type 1 requires. The fact that this question, how close are we, really, is being taken seriously, examined with the full rigor of physics and history and political economy and philosophy, rather than answered with comfortable narratives or dismissed as naive speculation. This is itself evidence of a civilization that has begun to develop the capacity for honest self-assessment. That capacity is not sufficient for Type 1, but it is necessary, and a civilization that lacks it will never get there. A civilization that possesses it and acts on what it reveals might. Hold all of this. Let it settle. Let the weight of the 0.73 rest in your chest without either flinching from it or trying to resolve it into something simpler. Because the discomfort of sitting with that number honestly, of feeling simultaneously the extraordinary achievement it represents and the enormous distance it implies, is precisely the discomfort that genuine civilizational self-awareness produces. And genuine civilizational self-awareness is precisely what the work requires. The lights on that horizon are real. So is the darkness above them and the stars beyond that, and the silence in which no other civilization has yet announced itself. Both things are true. Both things matter. Now we arrive at the deepest part of this exploration, the part that has been present in every layer we have descended through, but has not yet been named directly. The part that connects the Kardashev question to the longest perspective available to human thought. The perspective of deep time, of geological and cosmic history, of civilizations as phenomena embedded in the physical history of a universe that began and will end on timescales that make the entire span of human existence vanishingly brief. Because the question of how close we are to Type 1 is, ultimately, a question asked from within a very specific moment in time. A moment that is, by the standards of geological or cosmic history, essentially instantaneous. A moment that will look, from the vantage point of whatever comes after it, whether Type 1 civilization or the silence of a failed one, like the single second between midnight and 1 minute past in a year-long story. We exist in what the physicist John Wheeler called, in a different context, but with relevance here, a participatory universe. A universe in which the choices of observers matter to the outcomes. Whether Wheeler's specific quantum mechanical interpretation is correct or not, the metaphor carries enormous weight in the context of the Kardashev transition. The universe, as far as we can tell, does not have a predetermined outcome written into its initial conditions for the civilizational development of any particular species. The outcome depends on what the civilization does, what choices it makes, what values it embodies in its institutions, what it considers worth protecting, and what it is willing to sacrifice. That is both the weight and the gift of our position on the scale. Now consider something that the numbers alone cannot fully convey. Every civilization in history that has faced a transition of the kind we are currently attempting has done so without a map. The transition from foraging to agriculture which fundamentally restructured human social organization, population density, and ecological footprint over a period of roughly 10,000 years, was not planned. It was navigated, stumbling and blindly, by communities that had no framework for understanding what they were doing or where it would lead. The transition from agrarian to industrial civilization, which restructured the entire energy basis of human society and the global ecology within roughly 200 years, was similarly navigated without a map, through a combination of accident, ingenuity, greed, catastrophe, and occasional inspired institutional innovation. We are the first civilization in the history of this planet that is attempting a major civilizational transition while aware that it is doing so. We have physics, we have history, we have the measurement, the 0.73, the 173,000 terawatts, the gap, the obstacles, the timelines. We have the Kardashev scale itself, a conceptual tool that allows us to situate our current moment within a larger developmental trajectory and ask, with genuine precision, what comes next and what it requires. That awareness does not guarantee success. It is not a sufficient condition for Type 1, but it is a necessary one, and it is something that no previous civilizational transition has had available to it. The agricultural revolution did not know it was a revolution. The industrial revolution did not know, for most of its duration, that it was altering the chemistry of the atmosphere, or that the coal it burned was a finite inheritance. We know these things. We know the scale of what we are attempting. We know the obstacles, we know the stakes, and we know, imperfectly, incompletely, but genuinely, something about what would need to be true for the transition to succeed. That knowledge is a form of power that does not appear anywhere in the Kardashev calculation. It is not measured in watts. It is not captured by the formula K equals open parenthesis log P minus 6 close parenthesis over 10. But it may be the most important resource available to a civilization attempting the most consequential transition in the history of this planet. There is a historical parallel that deserves extended attention here, because it carries the weight of this moment with unusual clarity. In the late 15th and early 16th centuries, a small number of European navigators, beginning with Bartolomeu Diaz, who rounded the Cape of Good Hope in 1488, followed by Vasco da Gama, who reached India by sea in 1498, and then Ferdinand Magellan, whose expedition completed the first circumnavigation of the globe between 1519 and 1522, discovered, through direct experience rather than theoretical deduction, that the world was not only round, but navigable, that the oceans that had separated continents and civilizations for all of human history were not barriers, but pathways. This discovery did not immediately produce a world of enlightened global cooperation. It produced, first and primarily, centuries of conquest, colonization, and exploitation, so brutal and so far-reaching in their consequences that their effects are still being reckoned with today. The navigational technology outpaced the moral and institutional frameworks available to manage it by centuries. But it also produced, over time, something that would not have been possible without it. It produced the first genuine experience of the world as a single interconnected system. The first visceral, empirically grounded understanding that human civilizations, for all their diversity and mutual incomprehension, shared a common planet with finite resources and deeply entangled fates. That understanding was the seed from which, eventually, the institutional experiments of the 20th century, the League of Nations, the United Nations, the international trade system, the global health architecture, the climate negotiations, grew, however imperfectly and incompletely. The parallel to our current moment is not exact. It is never exact. But the structure is recognizable. We have made a discovery, or rather, we are in the process of making it, that is comparable in its civilizational significance to the discovery that the world is navigable. We are discovering, through the physics and the numbers and the hard experience of climate change and pandemic and technological disruption, that the planet is a single physical system, that its management is a shared responsibility, and that the institutional forms we have inherited from a world of separate nations are insufficient for the management task that our moment requires. That discovery will not immediately produce enlightened planetary governance. It will not quickly resolve the political fragmentation, the institutional lag, the governance gaps that sit between us and Type 1. History suggests it will be messy, costly, contested, and slow. History also suggests that the discovery itself is not reversible. That once a civilization has genuinely understood something about the nature of the system it inhabits, that understanding becomes part of the foundation on which future institutional development builds, however painfully. We have understood that the atmosphere is a commons. We have understood that the climate is a shared system whose management requires collective action. We have understood that pandemics move faster than borders. We have understood that financial systems are globally interconnected in ways that make national-only regulation insufficient. These understandings are contested, politically difficult, and often resisted by powerful interests. But they exist. They are part of the intellectual and institutional foundation of the early 21st century. And they did not exist 100 years ago. That is genuine progress. Not toward the watts of Type 1, toward the wisdom that Type 1 requires. The Kardashev scale cannot measure wisdom. It cannot capture the distance between a civilization that understands the atmosphere is a commons and one that does not. It cannot reflect the institutional learning embedded in the Montreal Protocol, or the scientific achievement embedded in the mapping of the human genome, or the philosophical achievement embedded in the Universal Declaration of Human Rights, a document that, however imperfectly realized in practice, articulates a vision of human dignity that transcends national sovereignty and asserts for the first time in the history of any known civilization that every human being everywhere has claims on the conscience of every other. These things are not in the formula K equals log P minus 6/10, but they are part of the actual trajectory of the species whose civilizational position that formula is supposed to capture. And they suggest that the picture of our progress is considerably richer and more textured than the single number implies. What does this mean for the question we set out to answer? How close are we to Type 1, actually? The energy answer is far, very far, centuries away at minimum, under realistic assumptions about the pace of technological development and deployment. The gap between 0.73 and 1.0 on a logarithmic scale is not a rounding error. It is a roughly 500-fold increase in power consumption, requiring infrastructure build-outs, governance innovations, and institutional developments that have no precedent in human history. The knowledge answer is closer than the energy number suggests, but the distance is qualitatively different. It is not a distance in watts, but a distance in understanding, institutional capacity, and collective wisdom. And unlike watts, these things do not have a simple additive relationship. They accumulate unevenly across generations through processes that resist both planning and prediction. The civilizational answer is, it depends. It depends on the 5 choices we identified: fusion, AI alignment, energy access, institutional development, and the meaning question. It depends on decisions not yet made. It depends, in the most literal sense, on what happens next. And the deepest answer the one that sits beneath all the others, and that the Kardashev scale at its best points toward without quite articulating, is this. The question of how close we are to Type 1 is inseparable from the question of what we choose to become. The scale is not a prediction. It is a challenge, not a forecast of where we will arrive, but an invitation to examine where we are, honestly and without comfortable illusion, and to ask whether the civilization we are building is worthy of the universe it inhabits. That question does not have a number, but it has an urgency that no number can fully capture. And it is, finally, the question that matters most. There is a lamp near you. You may have forgotten about it. It has been there since the very beginning of this story, since the first words placed you in a room with light falling on your hands and asked you to notice how small a fraction of the energy of this civilization that lamp represents. It has been burning quietly throughout everything we have explored, the scale and its inventor, the numbers and their implications, the physics of the gap, the politics of the transition, the governance of the commons, the silence of the universe, the historical parallel of navigators discovering a round world they were not yet wise enough to use well. That lamp is still there, and it looks different now. It looks different not because it has changed, but because you have. Not because any single fact about it is altered, but because the web of meaning in which it sits has been expanded so far and in so many directions that the simple object, a few watts of electrical power, converted to photons, illuminating a small circle of a room on a particular evening, now carries the weight of everything we have been through together. It is fed by a grid. That grid draws from power plants burning coal and gas and splitting uranium and capturing wind and concentrating sunlight. That grid spans continents, maintained by millions of workers, governed by thousands of regulatory frameworks, threaded through the political economies of dozens of nations. The fuel that powers much of it was deposited in the Earth's crust over hundreds of millions of years by organisms that lived and died before our ancestors existed. The wires that carry the current were smelted from ore in mines on multiple continents, drawn and insulated, and laid by workers in cities and deserts and mountain passes, according to engineering specifications that are themselves the product of a century and a half of accumulated electrical science. And all of that, the entire vast, intricate, historically improbable infrastructure of modern energy civilization, adds up to approximately 18 terawatts, roughly 1/10,000th of the sunlight falling continuously on this planet. A Kardashev value of 0.73 on a scale that reaches, in principle, to the energy of entire galaxies. Your lamp burns in that context now. It always did. The difference is that you can see it. This is what the Kardashev scale offers at its best. Not a roadmap, not a forecast, not a verdict on our success or failure. It offers a perspective, a vantage point from which the ordinary objects of daily life become windows into the full complexity of the civilizational moment we inhabit, from which the lamp on the table becomes a node in a planetary energy system, from which that planetary energy system becomes a measure of civilizational development, from which that civilizational development becomes a question about wisdom and governance and the long arc of a species trying, imperfectly and incrementally, to grow up. Nikolai Kardashev drew his ladder in 1964 in a world that had just come within days of nuclear war. The Cuban Missile Crisis was 2 years past. The anxiety of mutual assured destruction fresh in the air of every serious scientific institution on Earth. He drew it as a tool for finding other minds among the stars. He could not have known that 60 years later, the civilization whose position on that ladder he was implicitly describing would still be in essentially the same place, having moved by only a few hundredths of a point while building an internet, sequencing a genome, landing robots on Mars, and detecting the ripples in space-time produced by the collision of black holes a billion light-years away. Carl Sagan took that ladder and gave it numbers, gave it the precise decimal notation that allows us to say, with genuine mathematical meaning, that we are at 0.73 rather than merely somewhere below type 1. Sagan, who more than perhaps any other scientist of the 20th century understood that the power of science lay not only in its technical applications, but in its capacity to situate human existence within a larger context, would have understood exactly what that number means and exactly what it doesn't. He would have understood that 0.73 is not a condemnation and not a comfort. It is a fact. And facts, honestly faced, are the beginning of every genuine advance. The machine learning model published in Scientific Reports in 2023 projected that, by 2060, with a humble average annual growth rate in civilizational energy index of approximately 0.042%, we will have reached approximately 0.7449 on the Kardashev scale. That number, 0.7449, is, in its quiet way, one of the most sobering single pieces of scientific information produced in recent years. It says that in 40 years of continued energy development, including all the solar and wind deployment currently underway, all the battery storage, all the grid modernization, all the electrification of transport and industry, we will have advanced by less than 0.02 of a point on a scale where we need to advance by more than 0.25 of a point to reach type 1, and where reaching type 1 requires not 1/4 of the work, but roughly 500 times our current energy infrastructure. The numbers are not wrong. They are not pessimistic projections designed to dampen enthusiasm. They are what the physics and the data produce when you follow them honestly. And yet, and this is the note on which this story needs to end, because it is the note that is most true, those numbers do not capture everything that matters. They do not capture the rate at which human knowledge is currently accumulating. They do not capture the possibility that fusion, which has been 20 years away for 70 years and is now being pursued by dozens of serious private companies, alongside the great ITER experiment in Kardashev, France, might finally resolve that long-deferred promise within the lifetime of people currently alive. They do not capture the possibility, not the certainty, but the genuine possibility that the cost curves of clean energy, which have already produced changes faster than almost any mainstream model predicted, might continue to behave in ways that make the 2060 projection obsolete before it arrives. They do not capture the institutional learning embedded in the Montreal Protocol's success, in the recovery of the ozone layer above Antarctica, in the slow and imperfect but real development of international frameworks for managing shared global challenges. They do not capture the moral progress, however incomplete, however contested, however fragile, embedded in the Universal Declaration of Human Rights, in the expansion of democratic governance across much of the world over the past century, in the gradual extension of the circle of moral concern to include people and species and ecosystems that previous generations regarded as beyond consideration. They do not capture what it means that we are asking this question honestly, that we are measuring ourselves against a cosmic scale and refusing to look away from what the measurement reveals. Most of all, the numbers do not capture the fact that the 0.73, for all its humbling implications, is also a number that describes something genuinely extraordinary. A species that emerged from the same nuclear furnaces that forge every element heavier than hydrogen. A species that spent most of its evolutionary history in small groups on a single African savanna, unable to count beyond the fingers on its hands. A species that, in the geological instant of 10,000 years, invented agriculture and writing and mathematics and physics and medicine and music and law. A species that has looked up at the stars and understood, through the patient accumulation of scientific knowledge, what they are. A species that looked at its own civilizational position through the eyes of Nikolai Kardashev and Carl Sagan and Michio Kaku and Elinor Ostrom and Eric Chaisson, and found in that self-examination not just a measure of inadequacy, but a vision of what it might yet become. 0.73. It is a small number. It sits modestly on a scale that reaches toward the incomprehensible. It describes a civilization that burns fossilized biology for heat, that cannot yet manage its own atmospheric chemistry, that is divided against itself by borders drawn on a planet that does not recognize them, that possesses weapons capable of ending the project entirely, and has, so far, through some combination of wisdom, luck, and institutional improvisation, chosen not to use them. It also describes a civilization that knows all of this, that has measured itself honestly and found the measurement worth making, that understands the gap and has begun, however haltingly, to close it. The lamp near you burns with the energy of ancient sunlight, carried through a planetary infrastructure of staggering complexity to illuminate this moment, this particular evening, this particular room, this particular mind, encountering these particular ideas for the first time or the 100th. The sun, meanwhile, pours 173,000 terawatts of energy onto the surface of this planet every second. Most of it warms the oceans and drives the wind and lifts the rain and sustains the biosphere. A vanishingly small fraction of it passes through the glass of your window and falls on your hands. The gap between those two numbers is not a fixed quantity. It is a question. The most important question our species has ever been in a position to ask. How close are we to Type 1? We are close enough to see the shape of the path, far enough that the path will test everything we are capable of, uncertain enough that the outcome depends on choices not yet made, by people not yet born, in circumstances not yet imaginable, and aware enough, for the first time in the history of this planet's most complex species, to know that this is true, and to choose, in full knowledge of the stakes, what to do next. If this changed how you think about the civilization you inhabit and the lamp that burns at its edge, then the time was well spent. Thank you for staying all the way to the end of this.